Greetings. We will continue with the unit 7, and our task in this is to get acquainted with atomic photoionization process and how to get the if not all the measurable parameters, at least some of the important ones. Like I said, that when you perform a photoionization experiment, one always likes to do a complete experiment, and then you can certainly measure the cross section, which is related to the transition probability. You can also measure the angular distributions of the photoelectrons, and then you can also measure the spin polarization parameters of the photoelectrons, and only after when you make a measurement of all of these, you really do what is called as a complete experiment, because all of these measurements are compatible with each other. So we will set up the theoretical framework, at least to the extent of discussing the photoionization cross section and also the angular distributions of the photoelectrons. And in our previous class we discussed that photoionization, of course, is because electromagnetic energy is absorbed by the atomic system, by the quantum atomic system, and therefore the photoionization cross section will be related to how much of power is pumped into the atomic system by the electromagnetic field. So that is a parameter of interest from the point of view of the classical description of this process, and we will conclude our discussion on the classical description of this process, and then today we will also get into the quantum mechanical description of the photoionization process. So we know that photoionization cross section has to do with the photoionization probability, and this will naturally be related to how much of power is pumped into the quantum atomic system by the electromagnetic field. So we obtained this expression in our previous class, which is to evaluate the average power which is pumped into the system by the electromagnetic field, and we found that it is related to the imaginary part of the atomic polarizability. So this is the connection that we got in our previous class, and it is an important one because a lot of literature on photoionization process will refer to atomic polarizability, will refer to oscillator strengths and so on. So I am preparing the background so that you can become familiar with the literature in this field. And the polarizability, of course, is then related to some macroscopic properties like susceptibility, and then of course there is the quantum mechanical expression for the photoabsorption cross section, which also we will begin to discuss today itself. So this is the expression for the atomic polarizability. Alpha is the polarizability, d is the dipole moment, and we found that if you have you divide the modulus of the dipole moment by the modulus of the electric intensity to get this atomic polarizability, and if you have a certain number of atoms per unit volume in a dilute atomic gas, then you will have the susceptibility which is scaled from the atomic polarizability by the number of atoms per unit volume. So these are usual macroscopic expressions, and then the susceptibility is also related to the polarization properties of the medium. So now what I have done is to multiply and divide by the complex conjugate of the denominator, so that I can extract the imaginary part of the atomic polarizability. So that is the quantity of interest, as we have already recognized. So I have just multiplied and divided by the complex conjugate of the denominator, and then I can extract the imaginary part of this quantity, which is now this is the real part. So the imaginary part of the numerator is this gamma omega. Gamma is connected to the damping coefficient in our oscillator equation, and you can play with these terms a little bit, recognize that this is just the difference of two squares. So you can write this as a plus b into a minus b, and there is a whole square here. So you can rewrite these terms in somewhat simple form, and what we do is to extract the omega 0 plus omega as a common factor from these two terms. So, the second term in the denominator has to be divided by this omega 0 plus omega whole square, because that is the term which is taken as a common factor between these two terms. So, outside over here the sum of these two is not very different from twice the natural frequency. Inside over here the difference matters and we have to keep track of that. Okay, this is the usual approximation scheme that one employs, that you can always ignore small numbers, but only when they come together as additive terms to large numbers. So, that is all there is to it. So, now near the natural frequency you have these frequency terms omega, omega 0 s to be nearly equal, and then you have got an omega 0 square here, there is an omega here. So, you get a 1 over omega as a common factor, and then the rest of the factor which appears in the expression for the imaginary part of the atomic polarizability. Now, notice that this is related to the actual power which is being pumped into the quantum atomic system by the electromagnetic field, and you have a very simple expression which is coming from the imaginary part of the atomic polarizability. So, you plug in this imaginary part of the atomic polarizability in this expression and get this power which is pumped in terms of this. Now, some of you might already recognize the form of this function. So, I will just draw your attention to that, but you will quickly see what exactly it is. I have also referred to the relationship that you will find in Fano and Rao's book, which comes from chapter 2 of this book, because one of my objectives is to help you gain acquaintance with what is the most common literature in this field, and Fano and Rao's book is a classic one in this particular context. So, if you look at this form, you probably already recognize that this is a delta function. Now, delta function, the Dirac delta function has got very many manifestations. Okay, there are many representations of the Dirac delta function, not just the square block. You have got the sinusoidal expressions and various, there are several shapes, number of functions which conform to the functional definition of a Dirac delta function, and you will find most of them in Arfken's book. So, this has a form which is similar to a Dirac delta function, not surprising, because you know that the maximum power absorption is going to take place at the natural frequency of the oscillators. So, what we do is to introduce a definition of what is called as an oscillator strength, and this is a term which gets used in, which is borrowed from classical oscillator model into quantum mechanics as well. So, the classical oscillator model, it is defined in this particular form. This is the definition of what is called as the oscillator strength distribution. Notice that it is df by d omega, so it gives you some sort of a spectral distribution over various frequencies. So, this is the definition of what is called as an oscillator strength, and using this definition you can write the expression for the average power which is pumped into the atomic system by the electromagnetic field in terms of what we have now defined as the oscillator strength. So, the oscillator strength appears explicitly in this, and eventually it will get related also to the photoabsorption cross section. So, this is the definition of the oscillator strength, and it has been defined in a very peculiar manner, and there is a good reason for it which will become transparent very soon, that as you notice that this gives you the spectral distribution of the oscillator, and the photoionization cross section which we will get from the quantum mechanical expression, which will we will get into discussing that very soon. It will be related to this average power which is pumped into the system per unit intensity of the electromagnetic field, because you need to normalize it in a certain way. So, this is the relation that we will extract from our quantum mechanical description. In the meantime, I will let you find the dimensions of the power and the intensity and find out what are the physical dimensions of sigma that you expect, okay, and you must get them from both the quantum mechanical formulation as well as the classical formulation. So, this is your oscillator strength, and it is very similar to a Dirac delta function. This is the exact expression for the Dirac delta function, which satisfies the usual defining criterion of a Dirac delta. So, you see the connection between the Dirac delta and the oscillator strength. Notice that there is a factor of 2 over here. So, now if you want to integrate the oscillator strength over all the frequencies, you will obviously integrate from frequency 0 through infinity, okay, so that you have an integral over the entire frequency range. But you have got a factor of 1 over 2 which is included in the Dirac delta, but then you can extend this integration range from 0 to infinity to minus infinity to plus infinity, and you can do it without any hassle, because you know that the electric intensity of the radiation field was 0 at time less than 0, and similarly in this context, if you extend this range of integration from 0 to infinity to minus infinity to plus infinity, all you have to do is to take half of that integral, okay. So, this is a straightforward extension of the range of integration by doubling the range of integration and then taking a factor of half. So, you take 1/2 of this range of integration, but now you have got a factor of 2 here and another factor of 2 over here, which will cancel each other, and what you get is the integration of the delta function over the entire range minus infinity to plus infinity. So, you get a normalized value which is plus 1. Essentially what you discover is that the oscillator strength has been defined very appropriately, because by choosing this definition as 1 over pi times this factor, we find that the oscillator strength is so defined. This is the choice that we have made, and it is a very appropriate choice, because when you integrate it you get unity, okay. So, that is how it has actually been introduced. So, now we get into the quantum mechanical treatment, because now we have the terminology from the classical model of electrons which are treated like oscillators in the atomic system, which are bound to some equilibrium positions by spring constants. There is a dissipation, and we used essentially the model of a classical damped driven oscillator to get these expressions, okay. So, now we get into the quantum mechanical treatment, and you would have done part of this in your quantum mechanics course in the context of the time dependent perturbation theory, because that is the tool which we are going to use, but I will go through it very quickly. So, essentially we will have a simple treatment in which we will make use of the non-relativistic Schrodinger equation. We will work within the approximation of independent particle models, so that all the many body effects and correlations and all these other details that we know are important, they will have to be added on, but we will first develop the basic formalism for the simple 1 electron model using the non-relativistic Schrodinger equation, and then we can always plug in additional details like relativistic effects, correlation effects, and so on. So, all these many body effects, correlation effects, configuration interactions, and so on will then have to be added on later to our consideration, but this is just the starting point. So, our quantum mechanical problem here is this, that you have got an atomic system at it, there is a certain coordinate system which I will make use of, and this is in the presence of an electric driving field which is represented by this force F, which is a time dependent. This is the space and time dependence of the force. Essentially you have got the real part, which is the cosine term, and the electromagnetic energy is incident on the photon in a certain direction, and I choose this direction of incidence to be the z axis, and as a result of photo absorption, one electron, let us say, is knocked out of the atomic system, and it shoots off. It shoots off in what we call as a unique exit channel in terms of our ingoing wave boundary conditions. So, it shoots off in a particular direction. There is a certain unique direction in which it takes off, and let us say it takes off along a polar angle theta and an azimuthal angle phi with respect to the zx plane. Okay. So, we will use the cylindrical symmetry in this particular geometry. So, this is the physical process that we are going to be talking about. It takes off with momentum h cross k. So, this is the photoelectron momentum, and this is the photoelectron which is knocked out of the atomic system as a result of absorption of one quantum of electromagnetic energy, one photon. So, we consider again for the sake of our initial consideration that the electric component of the electromagnetic field is polarized along the x axis. So, this unit vector E is the same as the unit vector along the x axis, which is Ex. Okay. So, this is our geometry with reference to which we will develop the basic formulation. Subsequently, we can extend this treatment to unpolarized light or any other state of polarization. So, this is what is happening in photoabsorption. You have got a certain initial state, energy E0 and eigenstate represented by psi 0, and the photoabsorption raises it to a certain excited state. Now, the initial level is sharp and the final state will have a certain width. Okay. Now, this is characteristic of the uncertainty principle. Okay, but the uncertainty principle, you have to remember, this is the energy time uncertainty, and I did mention this in one of our earlier discussions as well, that the energy time uncertainty really appears on a very different footing than the uncertainty for position and momentum, because there is no operator for time in quantum mechanics. Okay. Q and P, when you consider Q and P as position and momentum, linear position and linear momentum, or angular momentum and angles, okay, any canonically conjugate pairs can be taken as Q and P. But these are dynamical variables which are quantized, for which you have operators, and then Q and P in quantum mechanics come out as eigenvalues of the position operator or eigenvalues of the momentum operator and so on. Okay. You do not get time as an eigenvalue of an operator for time. It is a certain parameter, but it still has the same sort of energy time uncertainty between the canonically conjugate variables, and because of this excited state has got a certain width which is represented by this. So, the energy actually is a complex number rather than a real number. Okay. Energies are typically real, these are real eigenvalues of a Hermitian operator. So, one should ask as to why does the excited state decay at all. If you have an atomic system and if it is excited from the ground state to an excited state, if the excited state is also a stationary eigenstate, it should actually have infinite lifetime if its energy is sharp, right, like the energy of 2s, 3s. Okay. It is the same as the energy of the 1s divided by n square. Okay. You divide it by 2 square, 3 square, 4 square, whatever it is, and you get a single number as a result of dividing 13.6 by 4 or 9 or 16 or whatever, you get a single number, right, and it is a sharp energy, and if it is a sharp energy level, it would have infinite life. Okay. So, there is something which is missing in this consideration, and I hope that you know what the answer is. If you know it, well and good, if not, give it a thought, and you should certainly we can talk about this in some other context. But over here I just want to draw your attention to the fact that in real atomic systems you do have these excited states which have got a certain width, and now you can set up the Hamiltonian for the quantum system together with the electromagnetic field, so that the generalized momentum is now P minus qa over c, right, and then what I have made use of is what is called as the minimal coupling. Essentially what it means that you are not taking into account the interaction between the field and higher multipoles of the charge distribution. So you have just the leading term. So this is the minimal coupling Hamiltonian for the interaction of a quantum atomic system with an electromagnetic field, and you can expand this term. Remember that P and A do not really commute. P is the gradient operator, so it will not commute with the vector potential operator A. So P dot A and A dot P will not be the same. So you have to take into consideration the del dot A and the A dot A term very carefully. There is also a term in A square coming from the scalar product of this operator A with this operator A. So these are some of the terms, and one would hope to use perturbation theory, and the whole contention of perturbation theory is that the perturbation is weak compared to the original Hamiltonian. So that is the most important thing, okay. And this is our generalized momentum. Notice that the vector potential has got dimensions of energy over charge. On the perturbation Hamiltonian, there are two terms in the perturbation Hamiltonian. There is a linear term in A, and there is also a quadratic term in A square, which we have seen in the previous expression for the Hamiltonian, right. The Hamiltonian inclusive of the perturbation, it had both the linear term as well as the quadratic term. So now if you take the ratio of the quadratic term to the linear term, okay, just order of magnitude estimate, it is QA over 2 twice Cp, okay. That is the rough estimate of the importance of the quadratic term compared to the linear term. And this is a very nice problem in Schiff's quantum mechanics, that if you take the magnitude of A and just for the sake of exercise take it for the visible part of the electromagnetic spectrum, because if you have radiation in a cavity you can estimate how much energy density is there, you can measure what would be the magnitude of A for such a cavity at a certain frequency, because you have got the frequency distribution formula from which is the Planck's formula, right. So you can get an expression for the magnitude of A for visible part of the spectral range, and you can take it for a cavity at several thousands of kelvins just to be on the safe side, because you want to consider what will happen if you have really strong high temperatures. And then for P, so that will give you an estimate of a number for A. Q and C are of course constants. This is the electron charge and the speed of light, and for P you can take the mechanical momentum of an electron in the Bohr orbit, okay, just to get some sort of an order of magnitude estimate. And if you find this ratio, you will find that the quadratic term is much weaker compared to the linear terms, and that is the reason you can really throw it, okay. So you certainly can throw it, but then there is this approximation has to be justified, and this is the way you discover that the quadratic term is ignorable. And in fact in weak fields you can ignore it. When the fields are very small you are led to 2 photon processes, and then you can use when you deal with lasers and so on, very high intensity radiation, then you cannot do this approximation. But we will work within the domain of the weak fields, and in this approximation the quadratic term can be ignorable. And using the same analysis, the same line of thinking, you will also find that the linear term is a small fraction of the original unperturbed Hamiltonian. So that now you convince yourself that perturbation theory can actually be used, okay. So we will throw off the term in phi, use the Coulomb gauge, and this is the del dot A operator. So let us not throw it yet, although in the Coulomb gauge the divergence of A, which is a scalar, which vanishes, but here this is the operator. This del dot A would operate on an arbitrary function of f, and then you will get the divergence of a product of two functions, a vector function A and a scalar function f. So you have to take the product of these two functions and take the divergence, and that will give you two terms. one of which will have the scalar divergence of A, which certainly can be thrown in the Coulomb gauge. Okay. So, this term would vanish, but the remaining two terms would add up, and now you have got the approximation for these two terms in the Coulomb gauge. This is exact, that in the Coulomb gauge these two terms add up to twice A dot del, and that is the equivalent operator that you can put in your interaction Hamiltonian, which is the perturbation Hamiltonian. Okay, so this is now your perturbation Hamiltonian, and we will make use of perturbation theory. The perturbation is time dependent, so we will make use of the time dependent perturbation theory, and you will expect to meet Fermi's golden rule in this context. So, this is our initial state, this is your perturbation, and we introduce an order parameter lambda. The only values of significance are lambda equal to 1 and lambda equal to 0. Okay. So, lambda is just a mathematical construct to develop the perturbation approximation, and you expect that the system wave function is now a linear superposition of the unperturbed states, but then you allow the expansion coefficients to be time dependent. In other words, you allow for transitions between various states. Okay. Because what the transitions will do is to change the occupation number of different states. So, the probability of occupancy of a particular state becomes time dependent. So, that is the idea over here. So, this is your system wave function. You are still working within the domain of perturbation theory, so that you do believe that your system wave function can be represented as a linear superposition of the unperturbed wave function. That is the premise of perturbation theory, that the perturbation is not so violent that it throws the system out of the Hilbert space that it originally belonged to. So, now all we do is to substitute this summation over here. This summation symbol k is generic, it includes summation over discrete states, and it will also include an integration over the continuum states, because the eigenspectrum consists of both the discrete part which converges to the series limit, but above the series limit there is a continuum. So, do not forget that. Okay. And in fact, in photoionization you do have transitions to the continuum. So, that is really important for us. So, you have got this expansion of the system wave function which is plugged into the Hamiltonian into the Schrodinger equation with the full Hamiltonian, which is h0 plus lambda times h prime, and the expansion coefficients are now time dependent. So, here you take the time derivative of a product of two functions of time, one is the coefficient c which is time dependent, the other is this e to the minus I omega t. So, you can do this derivatives very easily, and from the two sides of the equation you find that there are these common terms, because h0 operating on psi k will give you the eigenvalue equation for the unperturbed Hamiltonian. So, you can cancel these terms with what you have on the left hand side, and essentially you get a rate equation for these coefficients Ck. Okay. Now, let us extract the term for a particular final state. So, the way to do it is to take the projection of this whole equation on a state psi f. So, you just multiply it by psi f complex conjugate and integrate over the whole space, because that will give you the orthonormality condition between f and k, which will give you the Kronecker delta as delta f k. In case of the continuum functions, you will have the corresponding Dirac delta when you do the integration. Okay. But this whole treatment is generic. So, you multiply by psi f star complex conjugate and integrate over the whole space. So, you get only one term corresponding to k equal to f. So, here you have got the coefficient for c f dot, which is written over here, this is I h cross. This psi k with this psi f has given you a delta f k, and summation over k has given you a single term. You got the e to the minus I omega k equal to f. So, this is a minus I omega f t over here, and then you have got the corresponding terms on the right hand side, but when you project this right hand side on psi f, you get the matrix element of the Hamiltonian, which is the perturbation Hamiltonian in the states f and k. So that is the matrix element which will be a measure of the probability amplitude that the interaction H prime will induce a transition from the state k to the state f. Okay, so the probability of the process is going to come from this particular term, as you can begin to see. So this is actually a space integral, it is integration over r theta phi, and this is the matrix element which is of importance. So you get the expression for the rate coefficient, this is the coefficient and this is the rate at which it is changing with time. Now we again do a perturbation expansion of this coefficient, because in the perturbation theory you expect that this coefficient is expressible in a power series of the order parameter lambda. Okay, lambda is the perturbation order parameter. So you will have a certain 0th order approximation to that and a first order approximation and so on, and depending on how much detail you want to put into your perturbation theory analysis, you can do either first order perturbation theory or second order perturbation theory and so on. So you have an expansion in this order parameter. So here I have expanded this this coefficient c in terms of this perturbation order parameter, which is just a mathematical construct in our model. Eventually we will be interested in only limiting conditions, lambda equal to 0 is no perturbation, lambda equal to 1 is the full perturbation. So those are the only two conditions of physical importance. So we find what is the rate at which this coefficient changes with time. So you get lambda is an order parameter which is time independent, and you get the time dependent. So the dot represents differentiation with respect to time, and now you can plug in these expansions in this expression that we got from first order perturbations. Okay. So you got lambda on both sides of this equation, and certainly your analysis must be independent of lambda, it cannot depend on lambda, because lambda is just a mathematical order parameter that you have constructed. So you expect that terms corresponding to the same powers of lambda on the right hand side and the left hand side are equal. Okay, so that is a necessary condition which you can apply very comfortably, and by setting in the powers, the terms which come as coefficients of corresponding powers of lambda, when you take the 0th power of lambda, you get the coefficient, the 0th order coefficient, to be independent of time. Its time derivative vanishes, dc by dt of this 0th order coefficient vanishes, not surprisingly, because these will certainly not depend on time. But then when you do the same for first order terms, you get an expression for the rate at which this coefficient changes with time in terms of this matrix element, and now it is in terms of all the other coefficients which belong to the unperturbed problem. Okay. So you can really go ahead and use perturbation theory and get this particular factor. So you can continue this and by induction and get the expression for the time derivative of this coefficient for the s plus 1th term in terms of the previous one, and you can get all of these terms in this perturbation theory. Of course, one assumes in this that the perturbation actually converges. Okay. So the perturbation theory can be used whenever you cannot solve the problem exactly, but there are a number of conditions which have to be satisfied. First of all, the perturbation has to be really small compared to the unperturbed Hamiltonian, but then it is also taken for granted when you apply perturbation theory that the perturbation series will actually converge, which is not always really the case. So you do run into complex situations in real systems when you cannot use perturbative methods and you have to use some other methods. But here we work within the domain of first order perturbation theory, and we presume that the perturbation is switched on at a certain instant of time which we take as 0. So, T0 is equal to 0 at this particular instant of time, and at this instant of time we presume that the system is in a particular known initial eigenstate. What it means is that out of all of these infinite coefficients Ck0, there is only one coefficient which is equal to 1 and all the other coefficients are 0, okay, because that is the initial state which we presume is a known state. When you know that the system at the when you turn on the potential, the system is in a given quantum state, then you know that the expansion coefficient for that particular state is exactly equal to 1, because the entire probability is contained in that particular state. So, you presume that the system is in a known initial state I, which means that this coefficient is equal to 1 if k is equal to I, and it is equal to 0 if k is not equal to I. That is what it means, and you can plug in this Kronecker delta in this expansion, and then you get a single term on the right hand side. So, instead of this summation over k, you get only one term corresponding to the initial state k equal to I. So, this is the expression that you get for the rate at which this coefficient will change with time, and that will tell you the probability of occupancy of that level, because the probability amplitude is a measure, this coefficient is a measure of how that state is occupied at a given instant of time t. So, you take the derivative of this coefficient, and this is the equation that we have got. So, you can integrate this, right, you integrate it over time t, and you get a measure of the probability itself, which is just the modulus square of the probability amplitude, which will give you a measure of the transition probability to the state f from the state I, okay. And this transition probability is the first order transition probability. It is affected by a certain perturbation which we have already introduced earlier, okay. So, this is now our expression for the probability amplitude, and what you have in this are these integrals. There are these time dependent integrals. There is this integration from 0 to t, the time is a dummy label. So, I have used t prime instead of t just to indicate that you are integrating it from 0 to a certain time t. So, the time label is now t prime, and the time dependent functions to be integrated out are contained over here in this frequency dependent term, and there is also in this interaction Hamiltonian you have got a time dependent term here, okay. So, these are the terms which are time dependent, and you will have to focus the time integration over those particular terms. The rest of it is a space integral, okay. So, there are two integrations over here, integration over space as well as integration over time. So, let us look at the time integrals now, and the time integrals are essentially these functions, as you can see very easily from the previous term. I pointed out that there is a term here, there is a frequency omega t prime over here, and there is a omega t prime over here. This omega has got a subscript Fi, which comes from the energy difference between the final state and the initial states. So, it is the natural frequency of transition between those two states, okay. So, here this omega is the frequency of the radiation field. You have to subtract from it the frequency corresponding to the energy difference between the initial state and the final state, and these are the two time integrals to be evaluated. So, one is with a minus sign and the other with a plus sign. So, here we handle both of them together, the one is with a plus sign and there is a one with a minus sign, and these are the results of the time integrals. So, it is a very simple exponential function. So, you can integrate it quite easily. So, this is your integration with respect to time. Now, mind you, omega is a certain frequency of the radiation field which is a positive number, and omega Fi will either be positive or negative depending on whether you are looking at the difference of energy between Ef and Ei, but are you subtracting the energy of Ei from Ef or the other way around, the sign of this will change. So, at a given frequency only one of the two things is going to take place, right. So, at a given frequency you cannot have omega equal to omega Fi and also equal to omega equal to minus omega Fi. So, we will focus our attention on the absorption process. So, out of these two integrals there is only one that we really need to consider corresponding to the absorption process, and this while I was preparing these slides, this was a few days ago on the 7th of October. If some of you use the Google, you might have seen this picture, and in this picture Google showed this transition of an electron jumping from here to here, and this is not how quantum transitions take place. So, I thought that it was an interesting picture which Google posted, and I was very delighted to see that it was in commemoration of Niels Bohr's 127th birthday on 7th of October, but that is not how the transitions take place, and here we are talking about quantum transitions. So, the transition probability is given by this particular matrix element and a time integral, and now there is only one of the two time integrals that we have to consider. So, we evaluate this time integral and put the limits which are over t prime equal to t and t prime equal to 0, and you get rather simple expressions that you are quite familiar with these integrals. Okay. So, this is the expression for the first order coefficient that you get from time independent perturbation theory. Now, the transition probability itself is the square of the modulus. So, let us do that. So, this is the modulus square, and then you have this quantity multiplied by its complex conjugate which will go into the modulus square, right. So, that quantity is here multiplied by its complex conjugate, and together this product is what I have written as twice f. Okay. This is just a simple notation. You will recognize why this twice f function has been used, because once again you will find that the Dirac delta comes out of this particular form. Okay. So, that is the reason this factor has been isolated, because it makes our treatment very easy. So, in anticipation of that I have introduced this function f, and this is therefore the definition of f. Okay. F is defined by this relation. So, that twice f is equal to this quantity multiplied by its complex conjugate. So, okay. So, this is your expression for the modulus square of this first order coefficient. This is our definition of twice f, and we will be interested in transitions near resonance, near the resonant frequency, which is the frequency difference between the initial state and the final state. So, Ef minus Ei is the energy difference, that divided by h cross will give you the resonant frequency, and this difference between omega and this resonant frequency, whatever little difference there may be there, is what I write as omega tilde. So, it is this difference which comes in both of these terms, and this function, if you just work out this product of the complex conjugates, you find that it is given by this sine square theta over omega tilde square term, which some of you perhaps recognize it as a delta function already. Okay. So, this has got the form of the delta function, and that is the advantage of introducing it. So, this is pi t times delta omega. This is the omega tilde, which is actually the difference between the frequency of the radiation field and the energy difference divided by h cross between the two levels. So, this is now the square of the coefficient, modulus square of the coefficient. Notice that there is a time dependent term over here. So, if you take the transition rate, which is the transition probability per unit time, you will differentiate this with respect to time, okay, and that twice pi t, when you differentiate with respect to time, t will go away and you will get the transition rate, which has been written as W. This is the transition rate. It has got this square factor qa over mc square, then it has got the square of this modulus of the transition matrix element. This is the matrix element for transition, that this interaction induces a transition from the state I to the state F, and then there is this twice pi times Dirac delta function. Okay. You will expect this to be related to the absorption coefficient. Okay. And earlier in our class today, I had asked you to look at the dimensions for sigma. I had asked you to look at the dimensions for q over I, and ultimately the expressions that you get from this must agree with, even you should get the exact correspondence, the exact dimensional equivalence. So, it is a good exercise to find what exactly is the dimension of W, and good idea to get it from first principles. Plug in the dimension of q, plug in the dimension of A, plug in the dimension of M, plug in the dimension of C, right. Get it from first principles and make sure that you do not miss out on any term. Okay. So, this is the physical process that we are talking about, and we have found an expression for the transition rate, which is given by this expression. Now, the process we have considered is the following. We have considered the electric field to be polarized along the x axis. So, this is for a given direction of polarization, which is the unit vector epsilon caret, and then we also considered a particular photoelectron ejection in which an exit channel was identified to be along the direction of the photoelectron wave vector k. Okay. So, I carry this information as superscript and subscript on this transition rate, because this transition rate has been arrived at for a particular process that we have considered. Okay. When we consider unpolarized light, or when we consider possible photoelectron ejection in some of the other directions also, you need to integrate over these angles. Okay. So, this is some information that you have to keep track of, that we have considered the electric component to be polarized along the x axis and the photoelectron ejection to have taken place along the momentum direction k. Now, our interest will be in getting an expression for the energy absorbed per unit time in this process, but we need to normalize it with respect to the energy flux in the electromagnetic radiation. So, we need to find what is the energy absorbed per unit time, and we have to get the energy flux, which is the energy per unit area per unit time of the electromagnetic radiation, right. So, this is what gives us the differential cross section. Okay. It is differential cross section because it is with reference to photoelectron ejection in a particular angle. Okay. So, there is a certain solid angle which will contain the direction of photo ejection, and this d omega is the solid angle. This is with reference to this polarization vector of the electromagnetic field and the direction of ejection of the photoelectron, and the energy absorbed will be just this rate that we got in our previous slide. So, this rate must be multiplied by the energy itself, which is h cross omega, and you have to divide it by the intensity of the field, which is energy per unit area per unit time, right. So, this will give you the expression for the cross section for the photoionization process. Now, once you know the dimensions of this quantity, these dimensions multiplied by energy dimensions divided by the dimensions of energy must again give you the correct dimensions for the cross section. So, that is a small exercise for you. Now, you need to find what is this intensity. okay, intensity at the frequency omega. So, how do you get the intensity? So, you got the vector field which is given by this expression here, this is the cosine function, right, and in terms of the vector field you can get the intensity because the electric intensity is given by del A by del T in the del A by del T in the Coulomb gauge phi is equal to 0, right. So, the electric intensity is just the rate of change of the magnetic vector potential divided by C, that is the Gaussian CGS units that we are using, and then the magnetic field is the curl of A, right. So, this is the Gaussian, I am not using the SI. So, that is the most common system of units in atomic physics. So, the intensity is given then by the average value of the Poynting vector, and you have got E which you can get from A, you get H from the curl of A. So, all you have to do is to evaluate this cross product, get the Poynting vector and get its average value over one time period, and that will give you the electric intensity which turns out to be omega square over twice pi C A0 square, okay. That is how it comes out to be related to the square of the amplitude of the wave, okay, but then there are other factors and you cannot ignore them, okay. So, the intensity is given by this expression and you can then plug in this expression for the intensity in the expression for the photoionization cross section, and this is what gives you the complete expression for the photoionization differential cross section for photoionization in a particular direction kf when the incident light is polarized along the unit vector epsilon. So, I will conclude the discussion over here today. We will continue from here in the next class, and we will then extend this to get the expression for the total cross section for photoionization, and we will also integrate over all possible directions and different polarization states. If there is any question, I will be happy to take.
Omega square minus omega naught square, that you, I mean that when gamma tends to 0, that is a Dirac delta function. But when you applied in that particular integration, we never use the fact that gamma is going to.
No, the gamma which was used in that expression referred to, see, it is coming from damping, and remind yourself of what damping is, because whenever you say that okay energy is lost when because of friction, let us say, the friction is of course not an elementary force, okay. Elementary forces are only electromagnetic gravity and so on, and they are all conservative, okay. So, strictly speaking there can be no energy dissipation, which is good, that energy, that is why energy is really conserved. Now, the reason damping comes in is because there is dissipation taking place only because you have not set up the problem comprehensively. You do not have the atom to be completely an isolated system. See, you have solved the problem of, you have done the quantum mechanics of the hydrogen atom. It really takes me back to the question which I raised in the class, and I asked you to think it over, that if you have an atomic system in an excited state, it has no business to decay at all, it should stay there forever, okay. It should have infinite life, okay. Why does it decay at all? Why does an excited state of an atom decay? The excited state is also an eigenstate, it is a stationary eigenstate, okay, or at least if it is a stationary eigenstate, the stationarity means that del rho by del T vanishes, right. The probability density is not a function of time, and therefore the system will have infinite life. I am sure some of you are going to have this question in the YY exam, that why does an excited state of an atom decay at all? It is not meant to decay at all if it is an eigenstate of a stationary problem. The reason it decays is because you have really not solved the problem for the entire universe. You have separated the hydrogen atom as if the hydrogen atom exists by itself, and that is the thing in the universe and that is the only thing in the universe, there is nothing else. But then there is the rest of the universe and there is this coupling between the rest of the universe and this, and that coupling is something that you missed out in formulating your original problem. Your original problem was set up for a Hamiltonian which is p square over 2m plus a certain potential that never made any reference to the interaction of this atomic system with the rest of the universe. This is the unspecified degree of freedom. Okay. This is the unspecified degree of freedom, which is what appears in your classical problems when you have heat loss. When there is an energy dissipation, it is taking place because you have not taken into account these other degrees of freedom which are also interacting with the system. So when you set up an equation of motion, what you call as a free body diagram in classical mechanics, you do not have these additional degrees of freedom. Likewise, when you solve the Schrodinger equation for the hydrogen atom, there are these unspecified degrees of freedom, and those unspecified degrees of freedom are responsible for the fact that your excited state is really, strictly speaking, not a stationary eigenstate. Okay. So it has got a certain lifetime, and that lifetime is connected with the width. That is the uncertainty principle between energy and time. So it is coming from a completely different consideration, not because you have two non-commuting operators for energy and time. You do not have an operator for time. Actually there have been some attempts in the early days of quantum mechanics to introduce an operator for time. There are some papers in that direction, but to the best of my knowledge it has not led to anything very concrete and nothing very tangible has come out of it. So in quantum mechanics, time is not treated as an operator, it is a parameter, but there is an energy time uncertainty, and as a result of this you have these excited states which are coupled to the rest of the universe. Those are the unspecified degrees of freedom, and they manifest as damping, they cause decay of that excited state. Okay. So they correspond to the gamma d of the classical model. So I introduced the classical model only because the terminology of oscillator strengths is carried over into quantum mechanics, and the oscillator strength terminology comes from this very classical old fashioned idea that an electron is bound in an atomic system with certain spring constants k. Okay. We certainly know that that is not the case. Okay, that is not really quantum mechanics, that does not fit into our model, but it is precisely this idea which gives rise to the expression for the oscillator strength. In fact, oscillator strength is defined in terms of this, if you recall the expression for the oscillator strength. Okay. So the oscillator strength requires you to make use of this model, and unless one is really familiar with this, it is difficult to appreciate literature in this field, papers by Fano and so on. So that is the reason I spent some time discussing the classical model, and the idea of damping is related to the width of an excited state because it decays. Any other question? Okay, so thank you very much.